What the heck? Oh, look at this. Look at this. I can't delete it, and it's also supposed to be right there. Imagine, like, I have the iPad off. Oh, you're not wrong, actually. Chase, what did you do? Chase, what did you do? No, fix it. What did Chase do? Chase, what did you do? No, I'm screenshotting it. You only fixed half of it too, is the crazy part. Oh, you're not doing anything other than giving me a heart attack. What did we do last time we did it?
Does everyone have the lecture worksheet yet? Anyone don't have the lecture worksheet? There's still some, I think, at the back of the class, so if you don't have any worksheet. Remember to grab a worksheet when you come in. It's at the back of the classroom. Okay, so for those who just came in, make sure you have the class worksheet, which is at the back of the classroom. If you don't have one, come to me, and I still have a few extra ones. All right, let's get the lecture started. So today we're gonna dive into, I think, the last big block of the class content that I will be teaching you guys, which is around the analog signals. Today's lecture basically gonna be around the overview of the analog signals. But before that, we will talk also about the some logistics on the final project, as well as the final project proposals and what are we expecting for those things, etc. Which is, first thing first, we have like a homework due this Friday. And after this homework, I'm just gonna post the remaining 2 homework all at once. They're gonna be due, I think, roughly one week after, and then the other one basically after the spring break. So, feel free to work on it a little bit earlier than usual. And I hope by this point, everyone in the class have a team in the final project. If you don't have a team assigned yet, or if you haven't signed on the team registration spreadsheet on the class website, come talk to me after the class, and then we can figure it out for you. If maybe connect you with other groups that's currently missing one person, or picking one topics that you most interested in and talk to those groups and see if they can use some extra hands. But let us know as soon as possible if you still don't have a group. And we're gonna have, I guess, the first document of the project that's gonna be inside of your final project, kind of like a profile, which is the proposal. It will be due next Tuesday, and we will be having the proposal review with the teaching teams basically immediately. We will allocate basically 30 minutes per team, where you get to basically sit down with us, present your proposals and your project ideas, and we will be like going through the ideas with you to see how is the idea looking? Is it too hard, or is it or it can be a little bit harder, and which type of hardware you guys are going to need, those kind of things. And we will help you have like a more, I guess, appropriate 373 projects for the final project. And on that note, the whole review session will be starting next Tuesday's lecture time. So basically 3 p.m., we're going to have the first days to go from like 3 p.m. to 7 p.m. So that next Tuesday will not be class in this room, so do not come here. We reserve 2 rooms at BBB so that you can just come to us. I think during the lecture time, the 3 to 5 p.m. ones are basically the whole teaching team is going to be in one room, and then for the later part, it's going to be split into 2 parallel rooms. So if you finish early and you want to have more feedback from the entire teaching team, trying to sign up early on the sign-up sheet. We will put the sign-up sheet tomorrow on like the slots and the locations. We'll keep that sheet updated. So just put your team's number on the sheet, and then we'll be meeting you for those. Give you a little bit more background. This is a class handout that we put on the class website in case you haven't seen it yet. It's basically give you like a walkthrough of from how you develop the project idea, and then discussing with us, doing like a revision, and then what comes as or what type of ideas we're looking for, and how do we do the grading based on amount of complexity, or how complete the project is, so to speak. So we can quickly just scroll over. Basically, you're currently at this stage. At this stage, it's still okay to just think a little bit bold and wide, a little bit out of the box. We will try to pull you back during our teaching meetings, like review meetings. And some of the restrictions, please read these so that none of us get into trouble. If you have any like spinning devices, motors, etc., make sure they have some form of like contains mechanism. If you have any food, make sure they're not touching any toxic ingredients, basically not touching any electronics, because a lot of them have like leads inside of the soldering pads, etc. Yeah, this is a little bit surprised, but it seems like university doesn't allow any alcohol drinks inside of the property. So for those who want to do some, like, I don't know, drunk drive testing kind of projects, you got to do it outside of the cold weather. And just if you're trying to shoot something, make sure it's not too strong. If you're trying to use lasers, make sure you have, like, if it's a UV laser, you make sure you have like a container or like a shielding thing laid it out. And in terms of the project size, usually we trying to, so say if you have a group of n, usually we're looking for n+1 individually identifiable components within your system. So if you have like a motor, that counts as like one component. If you have, say, like an IMU sensor, that counts as one component. This is just give you like a rough sense of what kind of complexity of this entire system we're looking for. And these are kind of like a breakdown of each of the components we'll count towards. You will notice that the difficulty components comes almost like 50%. That's basically where the amount of components you use and how hard they are going to be counting towards. And on the right, this is like a very good project, like a pretty decent project reference score will be based on that scoring system. We have in total like a little bit over 100, so that everyone have a little bit budget to like margins to work with. And like a good one would be basically 88% project. Just some like basic stuff. You have to use the things you learn in the class, obviously. Some kind of communications. You have to use the bus interfaces, interrupts, GPIO pings, as well as what's going to be later taught today, the analog signals, and then the next lecture or two, basically ADC and DAC, analog to digital converters or digital to analog converters, etc. And yeah, this is also give you like a understanding of what type of devices count towards which type of difficulty level. If it's just a switch or one LEDs, that's kind of easy. If you have like more complicated, say like LCD displays that doesn't use a very easy serial communication protocol, then that could be considered as one of the harder ones. Also, we have the like a scale factor based on the team groups. So we basically, depends on number of components you use, each one have like a score of difficulty. We add them all together and then times a group-sized factor. In this class, this semester, we force everyone to have like a 4-people group. We have, I think, 3 5-people group at the moment. So for the 4-people group, the difficulty level would be times a factor of 0.7. For 5-people group, it's probably going to be 0.6. But we can discuss more on that. So a little bit more details on the calculations with some example. Another big part is how well the whole system work together, right? It's one thing that you have each of the individual components work on its own, but it's also, you'll be surprised how much work and time needed to bring all those components together, especially when you have, say, 5, 6 components, because chances are they might interrupt each other and influence each other's working during the integration, or they just messed up the orders, etc. So it actually takes more time than you would think for most of the time. So make sure you start thinking about how to integrate them together at a very relatively early stage. But these are just some descriptions on how or like which type of integration levels we're trying to looking for here. I think a good project is around like 6 or 7 here. That's like a pretty decent score already. And yeah, this we also give some on the novelty of your ideas and the solutions you have, as well as this is like a little bit long shot. We have like extraordinary technical achievements, and it only weights on top 4 points. So shoot high, but also know that if you're running late or have these could be the part you think a little bit less. But basically, it's going to be very hard to get 4 points on this, so don't take it personally. Basically, every several semester, we might have like 1 4 points in this class. And 3 points is going to be like a very, very rare case in the class already. So just something to think about. But shoot high, and then we'll see where you landed. And here, which is the first deliverable of next Tuesday, the project proposal. Let me show you some examples here. These are, this is like before revision. So basically you will have a few sections. First section is pretty much describe your project. It's always good to have like 1 or 2 figures here to just show what you mean by what you're writing, like the use environment or like type of devices, or it could be sketched, but sketch it well, I guess. But it could also be some pictures taken from other places. And you will list it that what are the major functions of the systems, basically what does it do, and based on what's input or output it has. So something like this. And describe the input and output of the system in terms of the components, not in terms of the signal yet. And the second section will usually be like a, you can move around these sections, but this is like a general idea or like a sample of a pretty decent or pretty reasonable proposal structure. Second is some form like a functional diagram. I think you guys should probably learn something like this before, right? Basically, what thing goes to which and does what. It's kind of like a block diagram of what's the function, like a function flow diagram, if that makes sense. And the next part will be like the component diagram. It's a little bit more detailed. Like it's still like block diagrams, but basically each block shows in the current design which components are connected to this system, which ones controls which, and then what do they do on like a very high level. And on this one, we will ask you to put down like a component list as well, so that we can. You don't have to go so deep into which brand of the sensor module you're looking for, but basically which type of sensors you're looking for, so that we are able to kind of have a feeling of how complicated this project is and which type of communication protocol, etc., are likely to be used for this project. And another thing is we can also check if we already have any of these modules in stock. Otherwise, we will, purchase something for you. Yeah, where were we? Proposal. Yeah, I think another thing it's worth mentioning is we're gonna have, because we have like a slightly larger group this semester, we're gonna have like a form of where is it? Okay, the member contribution forms. So it's only gonna be viewed by the teaching team, so you will not you wouldn't be seeing each other's evaluation, but basically gives like a basic idea of how much in terms of like percentage of workload each team member roughly contributed to the program. It's across evaluating. We're not trying to make you guys fight or anything, but just be honest and be normal in like writing up this type of evaluations. We will basically use it as, say if you have like a 4-people team, right? And then if, say, a member in the end averaged about 20% of the workload, then the final grades of your final project as a group doesn't change for other members, but for you, it's going to be slightly scaled down a little bit. So just as a reflect of how much work each team members are in that. But just make sure you do a reasonable amount of work. It's not like we have to hit 25%, but if you're like much lower than the others, say like below 20, then that's going to have some effect. But besides that, it should be okay. Any questions so far? Does everyone have a group now? Okay, perfect. So yeah, another thing, we will also you will also get trained on basically your presentation skills, and which is going to be happening later on during the demo sessions, obviously, but also based on the team you already have, we're going to do some quick lectures based on the type of sensors or type of communication protocols you choose during your final project. And each of you will give like as a team, probably give like 10 to 15 minutes mini lecture to the entire class, so that like the communication skills of every group or like for most of you guys, hopefully can be improved after this class as well. We're running through those lecture slides with you once you have like a draft, so you don't have to worry too much like if you have enough content, etc. We will be guiding you through those. So yeah. If there was no other questions, we were going to be jumping to today's lecture. Any questions regarding final project or team formation or, anything? Okay, perfect. So today, we're going to talk about the analog signals. Most likely, we're going to go through only the first part, basically the overview of the analog signals, what are they, and how do we deal with them, how do we read them on like a higher level into our digital system, which most of you will know, should probably know by now, it's a pretty binary systems we're working with. Also, in the end, if we have time, we will show a little bit like research work on working with analog signals. I know it's a very, very, very broad research domain, but just show something interesting to get you hopefully interested. Yeah, so basically, the physical world is analog, and these digital systems needs to essentially measure those analog quantities and then convert them into a format or data format that the digital system can understand. Okay, I think the worksheet is on the other table. That might be the wrong worksheet. I think that's left over from the previous, sorry. So yeah, basically, we'll be measuring the analog quantities, like the sensor inputs, sound waves. I think the sound is probably one of the most commonly encountered analog signal, although most of the signals are analog already, but those are the ones you interact more intuitively every day, because as you're listening to me, it's a analog signal. Also, we have some other like actuators we can output the analog signal. So analog signal can be both input and output from essentially digital signals. So how do we do that? We have what we call ADC, analog to digital converter, and DAC, the digital to analog converter. So on the top one, the analog to digital converter, you can think of them like a audio recording. Like for example, this microphone I'm doing right now, it takes the analog input of my voice and then did some sampling and then convert it into a digital format and then broadcast it through a speaker, which is using the digital to analog converter, which takes whatever data is being converted from the previous converter and then trying to reconstruct it into an analog signal and then broadcast it through essentially the vibration of the speaker. So this is, and in terms of like electronic devices or equipment, the top one, the oscilloscope, I hope you guys have all used that at the moment by now. Have you guys used that? Okay, perfect. So that essentially oftentimes is what you used to look at analog signals. Basically, that will be able to sample the analog signals and then show it on the screen so that you can do some analysis of it. Of course, they also do digital signals, but just analog signal is harder. And the bottom is a function generator or a signal generator, depends on how you. Basically, it's you give it a few parameters and it will output a analog wave based on. You can also, output square waves, but in this context, it outputs like a analog signal, usually in like some form of like sine wave into other devices, basically. Okay, perfect. So how do we do that? The first concept we will be using is called the sampling rate. This is currently talking about how do we take, or like just in general, how do we switch in between the analog signal and digital signal, particularly take the analog input and into digital form. So the sampling rate is the rate at which the amplitude values are digitalized from the original waveform. Some of the examples that commonly used example, for example, the CD sampling rate. I'm not sure how many of you guys still use that. That was like a, if you're into like hi-fi, I think people will still use that at some point because it's much higher sampling rates than the most of the digital format you will listen to, probably like MP3 or AAC if you use Apple. But basically, the sampling rate of CD is 44.1K sample per second. Any ideas or any guesses why they choose that? Yes?
Human hearing goes up to 20 kilohertz, so you need to do 44,000 because of the negative rate there.
That is very correct. So the human rate, or like human hearing is about like 20 hertz to 20K, and then this is what we will be using if we will a little bit explain on this why it's like 2 times, but basically using this sampling frequency, we're able to, in theory, reconstruct what we will call it like a lossless waveform. Obviously, the most lossless or original waveform will be the wave file, but once we sampling it at this frequency, we can still count it as lossless format. And then we have some like other medium quality sampling rates, for example, like 22K, which is still quite decent very decent for if you were just to listen to some vocal or something. And we also have the phone sampling rate. It's like more on the low quality side in terms of sampling rate. It's about 8,000 sampling per second. Any guesses on why the phone sampling rate is so much lower than, say, CDs or other forms? Any guesses? Yeah.
Is it less data to transmit over like a phone line?
Yes. So we could have like less data, but where it's only 8K? But we can still ensure all the data got transferred within this sampling rate. But that's one of the major reasons why they chose to use like a lower possible sampling rate, so that we can transfer more giving us set bandwidth, we can transfer more data or more people talking. But the reason why it's choosing like a much lower sampling rate is because humans talk in a much deeper voice, so that it turns out this frequency is quite enough for to cover almost all the humans when they're like talking normally. If you want to like scream like real high, then that's another story. Anyway, a little bit on why we use like 44.1K rather than just 20K hertz as a sampling rate to reconstruct a lossless or almost lossless waveform is basically because of this Nyquist-Shannon sampling theorem. It's a theory that basically a bandwidth limited analog can be sampled at perfectly reconstructed in terms of the not losing any frequencies. Perfectly reconstructed if the sampling rate of this current system is twice as the maximum frequency of whatever the sampling rate you're trying to do. So basically, if the signal does contain the frequency components larger than half of whatever sampling rate you have on your sampling system, then there will be there could be some like aliasing errors, which we'll show in a minute. And there's some assumption of this theorem. Basically, they assume like no noise or like clock jitter. So in theory, this will pretty much work if you have like twice of the frequency. But in practice, for example, in the oscilloscope, we will tend to, do like a much higher times. We will talk that in a little bit later to give you like more intuition. Those ones are not theory because it's not mathematically proved, but those are like the intuition of in the real world with the real data, what's kind of like a sampling rate you should be aiming for. But it's good to know that in theory, this is the sampling rate you could have that can reconstruct you a lossless signal. And give you some ideas what the aliasing is. Basically, this is a sample signal. Basically, each of the points meaning one data point. And can you just by looking at this graph and calculate what's the sampling rate of this system at the moment? So the x-axis is time in second, and the y is basically the amplitude level. Anyone finish the calculation? What's the sampling rate of this sampling system? What's the sampling rate here? Anyone? Yeah. 2 kilohertz? Exactly. It's 2 kilohertz because, yeah, you guys all know math. So second question here. What's the frequency of the sample signal? Any thoughts? Yeah.
Would it have to be under 1,000? I'm sorry, under 1 kilohertz because of the sampling here?
Okay, so just by looking at this waveform, what's the sampling? What's the frequency you will observe based on like a signal? This signal could be. Yeah. Yes, that's the most intuitive. So if we just connect them all together, that this sampled signal is essentially a 200 hertz signal. But it doesn't necessarily mean the original signal is 200 hertz, because if we assume that the sampling rate we have, which is 2K, is already above, and the original signal have the highest frequency of less than 1K, then this is the only signal that we're going to be. But if the original signal contains something like larger than 1K, then it's possible that it's something else. But we'll look at that in a moment. Let's consider another like kind of edge case. So what would this signal be, or what it could be? At this, I think it's the same sampling rate. So yeah. Any guesses? Yeah.
2 kilohertz.
2 kilohertz. That's a great guess. That's totally possible. So essentially, the sampling rate is exactly the same as the signal rate. So that could give you a practically perfect line. Any other guesses? Yeah.
0 if it's a DC signal.
Oh yeah, that's also true. So basically, it could also be like a DC signal, not necessarily 0, but it can also be like a DC signal. Just doesn't have any up and downs. So, which is why we need at least 2 times faster. Say if in this case we already have 2 different results that can come from the same sampling system here. For example, this one, or just a flat DC signal. And if we go back a little bit to here, if we have something that's like faster than 1K in the original signal, or in this case, it's much faster. So this signal will essentially give, using the same sampling rate of the sampling rate we have, will essentially have the same sample point distribution as the previous 200 hertz. So this, just to give you an idea of what like aliasing means. It means if you have higher frequencies. Any questions on this so far? Like why we need to at least have 2 times faster so that all the signals are captured within each of the frequency under half of that maximum frequency. Yeah.
Is there any way to do filtering so that this doesn't happen, or do you have to do that like in analog?
The question is there any way to like on the hardware, I assume?
To like filter the signal so that we don't accidentally think there's another.
That's a very good question. So actually, in practice, most of the devices you interact with, unless it's like super bare, they all have some form of like they call anti-aliasing circuits. It's essentially like a RC circuits. It's like a low pass filter, so that it will give you they will give you a number instead of a data sheet of what's the frequency range it senses. So anything say go beyond that, it will just use some form of like anti-aliasing circuits to cut it off. So good for you guys. Yeah, those things, most of those things have been taken care of. But just in case you're working with, I don't know, trying to build your own CD players or anything, yeah, these things are just, yeah, these are still pretty important. And yeah, but yes, they actually have those anti-aliasing circuits integrated. Yeah, and it can get messier than this. For example, this one. So it's going to be very hard to tell which type of frequency this is generated if we just like connecting all together. This is actually basically like 100 hertz plus 400 hertz, and then a 1.6 kHz laying on top of each other. And then it's sampled at, I believe, 4,000 hertz. So just so that you know, these things can get really messy. So like these aliasing issues can be much harder to work with if we have multiple signals, multiple frequency of signals lay over on top of each other. And this is usually the case for almost all the signals you will see in real life. And a little bit on what we actually use in the real world. This is give you like a understanding of, it's good to know all the frequencies information is being captured, but it's also good to know what the actual waveform look like on the screen, basically, while considering all the possible noises that can be introduced or within the signal. So this is what like intuition we had for like the oscilloscope sampling theorem. It's not a real theorem, just some experienced some intuitions based on experience. Basically, we will recommend usually at least like 5 times the sampling rate you have to whatever the analog signal you want to sample in real life. Because chances are they're not perfect sine waves together. And if you look at the oscilloscope, we can show you some. Can you guys see that? That says like 200 megahertz on top, and the bottom is a really, yeah, it says 5 mega. Yeah, here, 5 mega sample per second. So basically, what this tells you is this device supports up to 200 megahertz of the bandwidth. Anything that below 200 megahertz signal, it's going to be very comfortably be able to sample that. And the device itself is capable of doing up to 5 gig sampling rate per second over 4 channels, because it's a 4-channel oscilloscope. What that means is if you only have like 1 channel running, you can go up until like 5 gigahertz sampling, which give you roughly 25 times ish of the highest frequency you're able to sample on this device. If you do like four channel all at once, basically those sampling rate got divided into 4 channels, and each channel will be able to do like 1.25 gig sample per second, and that's about like 6.25 times of the 200 megahertz. So this is just give you some intuitions on when you're trying to choose your ADC sampling rate or ADC chips, if you want to be a little bit even faster than what we can provide on STM. These are the factors you should be considering. 2 is great, but in real life, do like 5 or like higher. Any questions regarding these, like the sampling rate? Okay, perfect. And a little bit on the ideas of the analog to digital converter ADCs. We're going to talk more in details on this, like how they actually works, but just give you an idea. It's essentially a device that converts a continuous time analog signal into most of the time voltage, into a discrete time digital values. And yeah, on the left, something like this, and goes to the ADC, it became something like that. Basically, data points that attach to each other. Depends on your sampling rate. So if we zoom in on that, if we do like a little bit, yeah, like a big zooming, I guess. Basically, this is also like a pretty low resolution system, but essentially those signals that's coming out of the ADC is a little bit of a stepped signals that connected to each other. So if we have like the perfect sine wave here, and then if we only use say like 3-bit to sample this value, then we have like a these little steps of values across the entire signal. Because we use 3-bit, there are roughly like 7 steps for peak to peak, and these resolutions can change based on how many bits you assigned to this ADC device or ADC chip. Say if we have a 10-bit system, then from peak to peak voltage, you have roughly 1,000 little steps, which will look pretty reasonably smooth. If you have like 12-bit, which is also quite common, then you have like 4,000 give or take. So yeah. Yes, so just give you some ideas of how they actually got calculated. We have this. Wait, where is? Okay, here we go. So basically, you can think of them. On the left, this is like the most intuition ones. We just floor everything down. We have the data, like the V that's being measured on the ADC input, and then the VRL or like VRH is basically the reference voltage low and reference voltage high. Because like when there's an analog signal coming in, we don't necessarily know what's its ground or like what's the reference of the signal. And then the high and low basically here that you set is giving a sampling range of your ADC channel. So this is the range that all those bits of resolution can be divided into, so to speak. For example, if we have 3 bits here, and we have like seven slots, and then we have say peak to peak 1 volt, then or like 5 volts in this case, then each of the step would be essentially 5 divided by 7. Each of the value increase or each of the 1 bit increased, that means a jump in voltage of 5 divided by 7. So this hopefully this will make the equation make a lot of sense. Basically, just whatever the measured value is minus the low value of the reference, and then times that with what's the steps it's currently being, what's the value of each steps means, and then they're going to be the floored version of this conversion table. And in this, like on the left, it's kind of like what people used to do, but then they realized that means like the top, the peak values are almost never reached. It's kind of like wasting a bit there. So what a lot of manufacturers do is basically shifting it whole baseline, shifting the ADC up by like 0.5. So essentially, we're doing like a rounding system here. Or you can also think of it as whatever value you calculated plus 0.5, and then do the same floor multiplication. Floor is basically the integer operations in your code. So yeah. Any questions on this conversion? So basically, depends on how many bits or what's the resolution you have on your ADC chip, and how you calculate based on a given input and the reference voltage values, what's the corresponding voltage value in this signal at that data point. Any question on this? Okay, cool. And we will have that whole process called like quantization. We will naturally have some quantization errors in terms of, for example, like the resolutions. It's essentially the number of discrete values that represents a range of the analog values. So one discrete value can represent essentially a small range of that, and it's the basically the hardware error of your quantization or your ADC chip in this case. And with more bits added, that basically means you have higher resolution and that error is going to be smaller. And if you want to have like a more quantization of the error, it's essentially half of the, plus or minus of the least significant bit of whatever the step you're taking. Yeah. Also, yeah, less bit, which means larger step sizes, which leads to larger error. I'll give you like some just graphics representation. That's essentially what this arrow going to look like. Do we have any questions on this? Okay, cool. And let me ask you to do a little calculation here. So given this, given this system that we have, what's the quantization error for a 12-bit ADC with an input voltage range from 0 to 3 volt? Yeah, talk to your neighbors and then let's share answers after 90 seconds or so. Not the worksheet problem yet. This is a different one. All right. Any thoughts on this? What's the quantization error in the system? Anyone? Yeah. 0.7 millivolts. 0.7 millivolt. Almost. Check the equation again. There's 1/2. Just exactly, it's half of that. So because we're doing like a plus and minus. So because it could be either way, but essentially, yeah. So that's the equation there, and then we just divide it by the entire range. The reference high minus reference low, and then divide it by the number of steps times 2 we have in the system. That gives the quantization, the maximum quantization error of like every given sampling point. Any question on this? Okay, perfect. So what do these sample values actually represent, and how we, basically chose what's the reference high and lows? Yes, do you have a question? Yep.
In the previous slide why'd you have to subtract 1 from it?
Why do we have to subtract 1? Oh, that's just because if you go to, for example, if you look at this, -4 to 4, but there's only 7. Oh, sorry, the previous one. Yeah, it's 3 bits, but there's only 7, slots between the 8 values that we have. Yeah, that's why we minus 1 in the equation. Yes, so yeah, we talked about the reference like basically the 2 reference values of this ADC sampling, and that kind of determines what the sampled values are. But how to decide which range to use, right? If we say have this signal, and then we chose the 2 reference voltage value to be that, then we're gonna end up with like a cutoff signals. So those would not make sense. And it also doesn't make sense if we have the range too big. That basically means we're losing a lot of the resolutions within this, within this sampling range, so that it's only, say if that's like a 10-bit, and then chances are only, 4-bit or 5 bits of the actual data is being, well, actually 8-bit or 7-bit of data is being used in that case. And like a more ideal case is you just have something that's slightly higher than the maximum value and something slightly lower than the minimum value. Those ranges are typically provided to you in the data sheet. They will tell you different modes of the operation, or like different, what's the expected output range, or the input range is taking. So you can use that as the beginning references, and then depends on how you actually wired up your circuit or how you're sending your data. Then you can then fine-tune that range based on that. So yes, so this is basically how we do the transfer from the voltage to binary. This is from like 0 to 4, and each of the steps essentially means 0.5 voltage here. And I think one of our classmates already mentioned, there are some like anti-aliasing filters in the on the ADC output on a lot of the devices nowadays. If it's one of the more modern ones, essentially it has a RC circuit that does the acts as a low pass filter. So anything that below that cutoff frequency will be able to pass this circuit. Otherwise, it's going to be blocked off, so to speak, so that those frequencies that's higher than what your system is capable of sampling would likely not entering the ADC chip you're working with. And do you need to condition your input? Basically, which is what we're trying to do that. It's still good to have, although with all those with the anti-aliasing functions built in on most of the ADC channels. There's a few reasons for that. One of the reasons is hardware being hardware. They're not perfect. So basically, the cutoff frequencies is usually determined by I'm not sure if you're familiar with this, but basically the dB of the signal, essentially meaning how big this signal is compared to the rest of the signal, usually used to calculate the signal to noise ratio. So for example, we usually characterize the cutoff frequency based on, in this case, if it's below -3 dB. So it's basically still good to have some additional protections or something in the hardware, in the software, to make sure you are sampling the right at the right frequency, rather than just purely rely on the ADC's hardware circuits does the job. Speaking of which, if we do like a mini exercise here, if we have like if we want to like have power point to be like 30 hertz, and then we have a value of 0.1 mu capacitor, how big of a resistance that we should be using in this case, if we were to achieve, if we were using this signal here? Have you guys learned RC circuit at all so far? How many of you guys, okay, how many of you guys never heard about this? Okay, how many of you guys heard about it or learned about it? Okay, that's nice. Okay, do your calculation. And then okay, anyone have the answer yet, or a little bit longer? The real only, like, you know, it's here, the equation you need to use. You don't have to calculate the complicated one. Okay, has anyone finished the calculation? Come on, I see a lot of hands when I talk about RC circuits. Anyone? Okay, all right. It's gonna be just, 53K ohms. You don't have to calculate. If we ever ask you to calculate this in the exam, we'll give you a heads up to bring a calculator. So that, yeah. I don't know yet. We'll see. Anyway, let's go into the data conversion example. A quick example here. So how do we go from like analog to digital? Essentially, this is like a workflow we want from like a very, very high perspective. We have like the physical phenomenon or like the physical signals in the real world, and then we have like a magic black box or black box. And then that turns into the discrete digital units that engineers can understand, right? So how we do that is basically we still have these physical phenomena and we have sensors, or we can also call them like transducers, essentially, a device that converts one form of energy into another one. In electronics, it's usually convert whatever signal is into either voltage or current, usually voltage, but can also be current. And then it goes to the sensors, and the sensors, are you okay? Okay. Converting into voltage and current, and that goes into the ADC chip here, and then got sampled in as a digital value, which goes to the software, and then software decide to do whatever, and then do something. So here gonna come the fun part. The transducers convert one energy into another, and then we're gonna ask you to do, this is like the worksheet problem. This is just like a definition of what a transducer is. sensors are generally considered as transducers, basically. And yeah, feel free to work together with your neighbors, basically, given this analog temperature sensor, and that's the like a curve of whatever a voltage means as opposed to the Celsius, and then answer all of these following questions. And we're talking 5 to 10 minutes, depends on how quickly you guys are.
It's going to be minus 196.
But that's a little. I don't think that's a true.
It'll tell you.
Wait, actually.
What about 5? No, what if we use the sample? There we go, you got
Using the whole like unit of time. Just rather than there's no second.
How do we get to the bit?
just like
It's one of the homework was every 3 minutes.
That's true.
Pretty sure there's no bad.
Yeah, you have to like, it's an accelerometer, and you have to like, register output values.
for the function. What might be
My brain's going.
Yeah, that's what I was asking. think it's not just that'd make a lot more sense now.
It is.
It's like, okay, so your math is.
Well, like, I guess.
So like,
You said like your
the highest value of your EECS output.
yeah, because that's the range. The like previous problem last year was the range.
Plug it in the top value, plug in the slope.
I don't know how it works.
That's how we do it.
I know. It's because it's valid until 1.4, but you're measuring from 0 to 3.3, and so you actually in short,
What is the 50C adjustment?
So that's the value set by each value. So you have the step sizes.
oh, I know what you guys are saying. No way, I don't see what you guys are saying.
So basically, I took
For 2, I assume you use MC,
and then I divided.
convert,
Yes, that's right.
I think they just want converting ADC to temperature, considering they say
yeah,
ADC
but
temperature.
so which one of those is temperature? I assume you temp C
Yeah, that's it.
and so temp C is temp.
Yes.
And so you need to go from C value
Trying to go from
to
ADC.
and then
Oh, is that true? I actually. Yes, then you just plug that.
But you gotta alright.
But this is good. I mean,
Yep. 100%. It wasn't an ambiguous question whatsoever. Both of us, or
yeah, we just gotta plug that in.
this is, I convinced them that I put the right answer too. Yeah. Well, it's just 50 Celsius, and I plugged it in here, there.
Yeah, it's because it's the temperature, not the humidity. So it's gonna.
This equals 3.3 over 10 it's because Arvid asked the question.
Yeah, because like, yeah, it's a range. It's another range thing, but it's like index.
It's a fence post there because you gotta be able to index here, you gotta be able to index 3.3. So the number of values from that, because you only go from 0 to 2 and minus 1. So the number of values between that will be, or the number of gaps. Five. Sticking with it. I think that's 1.4. It's gotta be more than 2 times the, whatever it's called. It's gotta be more than equal to what you calculate. I thought you were thinking about that sample. There were 2 samples, like how much meter samples it has. So I'm talking about the emitter only and the receiver density how many samples it's you guys know what I'm talking about.
All right. How are we doing? Have you all almost finished? Okay, so what's the minimum step size of this ADC? Anyone? What's the minimum step size of the ADC? Yes?
0.0032.
That is correct. So yeah, so 3.22 millivolt. What's the transfer function you will need to write in your code? Essentially, you don't have to write the actual code, but just like one function formula. Or anyone have answers or how you're approaching this this question? Yes.
Just solve that equation for temperature and C. So you subtract 0.986 and then divide everything by 0.0035.
Yes, and but like the V temperature in this case is it's going to be sampled by the ADC, right? So you have to convert that into an ADC value, and it's a 10-bit ADC value. So basically, essentially, that's the equation we have there, and then we have the ADC value of whatever the ADC value. Say we have like a 10-bit, and it's usually just integer. So we have a the ADC reading from 0 to 1023, and each of the number represents a voltage value from 0 to 3.3 here. So just combining whatever you come up with there, and then you can have the ADC value here, and then you apply that ADC value onto the raw functions where you calculate the voltage and the corresponding Celsius in temperature, and then we have essentially this one. Does this make sense? So basically we have, yeah.
I just had a question for the previous one. Why do we not do 2 to the 10 minus 1 for calculating the step size?
Oh, yeah, we should do 2 to the 10 minus 1. My bad, I'll change that. But I think that the answer should still be the same, I hope. But yeah, it should be minus 1, sorry. Anyway, yes, anyone have any question on question 2? I know sometimes it's a little bit confusing when you have these minus 1 or versus non-minus 1, but in practice, when you have like 12-bit or 10-bit, this 1 point, it usually doesn't matter that much. It's 1 out of, but that's a good point. We should be accurate. Yeah.
Why would it be 2 to the 10 minus 1? Because it's not, we don't have a signed value calculating, so we would just use the full range, right?
Yes, it's pretty much because we say we have 5 values on a scale, and then there's only 4 steps between this. So yeah, but just like PWM, 1 more, 1 less usually doesn't matter that much in practice. but it's good to have it right. Anyone have any question on the question 2? Okay, good. So for the next part, what's the ADC value at 50 Celsius? Anyone? I see a bunch of you already finished up until question 4. Anyone want to share their answers on the question 3? Okay, we can also always go through it together. So basically, we have the ADC values here, and then because the T temperature is 50, we just put that into the equation we had from previous slides, and because the reference value is 0 to 3.3, which is peak to peak 3.3 volts, and then we get the ADC value to be 361. Do you guys get this right? Okay, cool. Just not sharing with me, but okay. What's the question for? What's like the approximate sampling frequency would you use? When you say your answers also include some like example use cases or like scenarios you're thinking about. But this is like a very open question. Any ideas? Any guesses? Any thoughts? Yeah.
Would it depend on the environment that the sensor is being placed in?
Yeah, that depends on like how fast you want to keep your the temperature updated. Say if we want to measure this room temperature for whatever reason, for like thermostats or whatever. What's like a sampling rate you would propose? There are a lot of numbers. You can just pick one, So if we were to measure the temperature of this room, what would be the sampling rate you guys chose?
Like half a hertz.
Half a hertz. Yeah, that's a pretty reasonable approach. I think, yeah, half a hertz, 1 hertz. If you're lazy, you can also do like, I don't know, 1 per minute, but that would be too slow. But anyway, somewhere 1 hertz is pretty reasonable for such tasks. If you want to do like more temperature sensitive environment controls, first you should probably not use this sensor. There's like other better sensors out there. But if you want to do that, you can also do like tens of hertz. Depends on how you approach it. Yeah, I was going to talk about some cool research stuff we did, some words before. Just get us through. When you work with analog signals, if you are not sure about what's the range you put, you can always implement some sort of like auto calibration to look at the signals and then decide the sampling range on the flight. Just something cool to show. Also, these are examples we did. Yeah, there's also like not all these signals, not all the noises are bad. You can also use like noise to be sensing different objects, for example. This one, the EM sense, it look at the electromagnetic noise the device generates, and then just do a bunch of classifications. So yeah, this is the recap of the class. And have a good rest of the day. This is the class. Thank you. And research is fun. It's very important. Please remember to write your names on the worksheet and then put it on the table before you leave. Thank you.